Hi friends, this is Rashekar, a GET faculty for electrical machines. In this video, we are going to discuss about construction of transformer core. How we can construct the transformer core, right? Let's see. For example, this is my transformer core. What is the purpose of transformer core, first of all? What is the purpose of this transformer core? The purpose of transformer core is first one, to provide accommodation for the winding, to provide accommodation for the windings, accommodation for the windings is the first most important. And next very important thing is that the transformer core provides a low reluctance path for the flux. The transformer core, it provides a low reluctance path for the flux. This is very important thing, the purpose of transformer core. So now we have to construct this transformer. Which material is preferable? This is very important thing. Which material is preferable? Generally, before the construction of transformer core, what are the considerations? It should be less losses. How we can construct the core? The core should provide less losses, less loss component. So now we have to discuss about what are the losses in the transformer core. What are the losses in the transformer core? The losses in the transformer core are two types. One is the hysteresis losses, and other one is the eddy current losses. Hysteresis losses and eddy current losses. So during the manufacturing of this transformer core, we should minimize the hysteresis and eddy current losses, then only the core is perfect. So now we have to discuss about what are the hysteresis and eddy current losses and how we can reduce hysteresis and eddy current losses. Then that is the process to construct the transformer core. Okay, so let's see what is hysteresis losses. Let's see what is hysteresis losses. Tell me, what is hysteresis losses? What is hysteresis losses? So once see what is hysteresis losses. First of all, we are going to discuss about hysteresis and eddy current losses. In that, first one, hysteresis losses. Hysteresis losses. So, see here, in generally, for every transformer, we are giving AC supply. We are giving AC supply to the transformer core, right? For example, in my transformer, I am taking one graph. Flux density on y-axis and magnetizing current or flux intensity on x-axis. Flux density and magnetizing current are flux intensity on x-axis, which we are giving the AC supply to our transformer. We are giving AC supply to our transformer. Let's see here, AC supply is nothing but, here the flux is 0, here the flux is 0, gradually the flux is increasing and maximum here, and again gradually decreasing and again 0, and again gradually increasing in reverse direction and again gradually decreasing to 0. This is called magnetization. This is called demagnetization. This is called reverse magnetization. Reverse magnetization. And this is called reverse demagnetization. Reverse demagnetization. This is actually what we are doing. When magnetization takes place, the flux 0 to maximum, as usually the flux density also increasing from 0 up to maximum. Increasing from 0 up to maximum. This is the flux density maximum. This is the flux density maximum, increased up to maximum. Then after, see here, when it reaches to maximum point, then after again it is in demagnetizing stage. During this demagnetization, the curve is like this and struck here. See here, simply this is magnetization and this is demagnetization. Demagnetization, nothing but the magnetizing current increasing up to some level, then after again decreasing to 0. Decreasing to 0. The current, not voltage. The current decreasing to 0. When magnetizing current is 0, flux also 0. If the flux is 0, the flux density should be 0. But here the flux density not 0. Here the flux density not 0. Actually, here my magnetizing current increasing, then flux increases, flux density increases. Then after, my magnetizing current decreases. If the magnetizing current decreases, flux decreases to 0, but the flux density not 0. Flux density not 0 due to residual flux phenomena. Due to residual flux phenomena or due to magnetic inertia of the transformer core. Magnetic inertia of the transformer core. Now, this phenomenon is called, which opposing the flux density to 0. This phenomenon is called retentivity. This phenomenon is called retentivity. Retentivity is mainly due to magnetic inertia. Retentivity is mainly due to residual flux. So the flux density not comes to 0, due to magnetic inertia. If you want to come this 0, if you want to 0 flux density, because we have to go for reverse magnetization. The reverse magnetization should be start at 0 condition. But here the flux density not 0. To bring it to 0, we have to apply some extra energy. We have to apply some extra force. That extra force is called coercive force. That extra force is called coercive force. By applying the coercive force, nothing but this I mu is increasing in negative direction. When the I mu is 0, my flux density is here. If I mu increases in negative direction more and more, at some condition, this flux density comes to 0. This flux density comes to 0. Now you can do reverse magnetization. So let's go for reverse magnetization. starting here, and this is in reverse magnetization up to maximum. This is a magnetization, this is a demagnetization, and this is a reverse magnetization, reverse magnetization. Then after again reverse demagnetization. During the reverse demagnetization, again same phenomena. This is a reverse demagnetization, reverse demagnetization. Here again, due to residual flux, it not goes to zero. This phenomenon is called retentivity property. To overcome the retentivity, to overcome the residual flux, we have to apply some extra energy. It's a coercive force. When coercive force is given, then it comes to zero. Then it comes to zero. Then after, again the magnetization. Again magnetization. This is an initial curve actually. This is an initial curve. Now this is magnetization, demagnetization, reverse magnetization, reverse demagnetization. This is one complete cycle. One cycle, one loop. Number of cycles, number of loops. Number of cycles, number of loops. This is called BH curve. This is called BH curve or hysteresis curve. In this hysteresis curve, the height of the curve given by, they will ask you a question, the height of the curve given by flux density, the width of the BH curve, the width of the BH curve given by, core volume, magnetic core volume. The volume of the, or area simply, the volume of BH curve, gives us, tell me, the volume of this BH curve gives us the hysteresis losses. The volume of the BH curve gives us the hysteresis losses. If the BH curve is linear, then hysteresis losses are zero. If the BH curve is linear, because they are linear, nothing but a single line, its volume is zero. If the volume is zero, hysteresis losses also zero. Hysteresis losses also zero. This is possible in air core transformer. In air core transformer, BH curve is linear. Hysteresis losses is zero. It is called an ideal transformer. Okay, so the volume of the BH curve gives us hysteresis losses, and the number of cycles is equals to number of loops. So the number of BH loops decided by number of BH loops decided by number of cycles. Number of cycles is nothing but frequency. Yes or no? Right? So this is about the BH curve. What is hysteresis losses? The volume of the BH curve gives us hysteresis losses. Sir, give a statement. What is hysteresis losses? Hysteresis losses nothing but the losses occurs in the magnetic core during the reversal of magnetization. The losses occurs in the magnetic core. During the reversal of magnetization. This is what hysteresis losses and BH curve. Sir, how we can control, how we can reduce this hysteresis losses. How we can reduce this hysteresis losses? Tell me, sir. The hysteresis losses reduced by low hysteresis coefficient material. Low hysteresis coefficient material. Let's see, generally the formula for hysteresis losses. The formula for hysteresis losses is equals to some constant, Steinmetz constant. This is neta is the Steinmetz constant. Some constant into, generally this is a volume, height to width and length, right? So from this here, neta into B max whole power x into F into V, neta into B max whole power x into F into V. Here V is the width and B is the height into width. We can get the area or a volume. But for example, if you have a 50 cycles, then hysteresis losses multiplied by 50 of one cycle. That's why frequency also multiplied. Yes or no? For one cycle, 10 watts. But my frequency 50 hertz. What is the losses? For one cycle, for one loop, 10 watts. For one cycle, one loop. For one loop, 10 watts. But my frequency 50 hertz. For 50 hertz, nothing but for 50 cycles. 50 cycles, nothing but 50 loops. So we have to multiply this losses with again frequency. So neta into B max whole power x into F into V. This is generally the formula for hysteresis losses. Formula for hysteresis losses. Here, x is the hysteresis coefficient. Hysteresis coefficient. X is the hysteresis coefficient. Generally, the hysteresis coefficient value 1.5 to 2.5 in the range. 1.5 to 2.5 in the range. If the hysteresis coefficient value is minimum, then automatically hysteresis losses also minimum. Automatically hysteresis losses also minimum. If the hysteresis coefficient is minimum, then hysteresis losses also minimum. Sir, for which material hysteresis coefficient is minimum? Then for silicon steel. For silicon steel, the hysteresis coefficient value is 1.6. Minimum value 1.6. 1.5 may not possible. So for silicon steel, the hysteresis coefficient is 1.6. That's why 1.6 is a minimum value. If this is minimum, hysteresis loss also minimum. Like that, we can control the hysteresis losses. Now tell me, the transformer core made up of silicon steel. Silicon steel. This is simply about construction of transformer in that hysteresis losses. What are the hysteresis losses and how we can reduce hysteresis losses? Right? Thank you. Hi friends. We are going to discuss about eddy current losses. Let's see, first of all, what is eddy current losses? Some people says the losses due to eddy currents. Right? Very good. Still, the losses due to circulating currents. Eddy currents or circulating currents, both are same. Sir, why the circulating currents are there? Why? What is the reason of that? So let's see here. Let's see here. For example, this is my transformer core. This is my transformer core. My transformer core is like this. A BCC structured. This is my transformer core. Of course, we have a winding here. Of course, we have a winding here. We are giving supply to the primary winding. We are giving supply to the primary winding, of course. Here some flux produces, of course. We are giving AC supply. AC supply. This is a moving flux. So now we have a moving flux. Now we have a moving flux. This flux also links with our transformer core. This flux also links with our transformer core. Nothing but the transformer core is a stationary conductor. The stationary conductor links by the moving flux. The moving flux and stationary conductor, what is the result? The result is the EMF. The EMF induced in the core. The EMF induced in the core. This EMF is not connected to the load. That's why this EMF is called eddy EMF. This EMF is called eddy EMF. The EMF which induced in the transformer core is called eddy EMF. Of course, the EMF induced in this core, and this core having many closed paths. EMF is there and closed paths also there. Then what happened? Some currents will circulate in the core. Some currents will circulate in the core. Those currents are called circulating currents or eddy currents. These are called eddy currents. When these currents are flowing through this transformer core, then some losses will take place, that is called eddy current losses. Due to eddy currents, the losses will take place in the transformer core. This is the core resistance. This is the eddy currents and this is the core resistance. Then some losses will take place. Those losses are called eddy current losses. So the losses due to eddy currents or the losses due to circulating currents is called eddy current losses. Yeah, now you know that eddy current losses. What is eddy current losses? How we can reduce them? How we can reduce this eddy current losses? Simply by increasing the resistance value. By increasing the resistance of the core, if the resistance of the core increases, automatically eddy currents reduces. If eddy currents reduces, automatically eddy current losses also reduces. How we can increase the resistance of the core? Generally, the core made up of steel material. For this, I am adding a semiconductor. Steel is a conductor. For this, I am adding a semiconductor. When this silicon is added to the steel, then due to semiconductor property, its resistance value increases. When resistance increases, eddy currents reduces. When eddy currents reduces, eddy current losses also reduces. Sir, how much percent of silicon added to the steel? Just 4 to 5% of silicon is enough. 4 to 5% of silicon is enough. Sir, you are saying that if silicon added to the steel, eddy currents reduces. So I am going to add around 20 to 25% of steel. Then what is the problem, sir? Then what is the problem? If more silicon added to the steel, if more silicon added to the steel, then its reluctance changes. The very important thing than the reluctance, brittleness also increases. Brittleness also increases. If brittleness increases, what happens, sir? If brittleness increases, the core gets breakdown at high voltages. So don't exceed 4 to 5%. Don't exceed 4 to 5%. If you add the 4 to 5% of silicon to the steel, then eddy current loss also reduces, and for this material, hysteresis coefficient also less. If more silicon added, its brittleness increases. Remember this. Right, sir. Next. This is the one method, and also by using laminating plates, by using laminating plates, also we can control the eddy current losses. By using laminating plates also we can control eddy current losses. Yeah, sir, we know that. Sir, what is laminating plates? What is laminations? Tell me. What is laminations? Laminations nothing but a thin parallel plates. Laminations nothing but a thin parallel plates. Sir, thin, how much thickness? The thickness of the laminating plates, is 0.35 to 0.5, 0.35 to 0.5 millimeters. 0.35 to 0.5 millimeters. Nothing but this is for 50 hertz of supply voltage, and this is for 25 hertz of supply voltage. 25 hertz of supply voltage. 0.35 to 0.5 mm of thickness the plate should be. Right? So this is laminating plates. By using laminating plates also we can reduce the eddy current losses. This is more convenient. So this is simply the eddy current losses. Sir, what is the formula for eddy current losses? Eddy current losses formula, some constant K. B max whole power 2. B max square into F square into T square. B max square into F square into T square. Here T is the no, it is not a time duration. It is a thickness of the laminating plates. Thickness of the laminating plates. If the thickness doubled and frequency halved, then no change. No change. I will give you problems on this formula also. So this is the formula for eddy current losses. Eddy current losses and how we can reduce them. Okay. So this is simply what is eddy current losses. Thank you. So finally, in this video, conclusion. How we can construct the transformer core. Let's see. So generally, first of all, I said you to reduce the hysteresis losses, the transformer core should be made up of steel, of course, some 4 to 5% of silicon. 4 to 5% of silicon added to the steel to reduce the eddy current losses. And also, we have to make it laminations. So finally, the transformer core made up of silicon steel laminations. What is the thickness of lamination? The thickness of lamination is 0.35 to 0.5 mm. So this is generally the transformer core made up of. But another main important thing is that the transformer core should provide low reluctance, high permeability. Low reluctance, high permeability. So what can I do to get this? To get this, I have to do CRGO. Cold rolled grain orientation. I have to do orientation. Grains should be oriented in particular manner. Grains, for example, if the grains are like this, there is no perfect magnetic path. If these grains are oriented like this, then high permeability, low opposition, nothing but low reluctance, reluctance nothing but which oppose the flux, there is no opposition. This is called grain orientation, cold rolled grain orientation. What is the purpose of cold rolled grain orientation? Low reluctance and high permeability. Low reluctance and high permeability. This is finally the transformer core made up of CRGO silicon steel laminations. Now they will ask you a question. What are the properties? What are the properties of transformer core? What are the properties of transformer core? Tell me, what are the properties of transformer core? See here, first one, low reluctance. First one, low reluctance. Second one, high permeability. Low reluctance and high permeability. And third one, why we are adding 4 to 5% of silicon? To increase the resistance. Yes or no? If resistance increases, eddy currents reduces, eddy current losses reduces, right? So third one, high resistivity. Yes sir. And next one, why we are choosing this steel only? To reduce the hysteresis losses, because low hysteresis coefficient, why we are not exceeding 4 to 5%? Because brittleness. So low brittleness, these are the properties of our transformer core. High permeability, high resistivity, low reluctance, low hysteresis coefficient, and low brittleness, less brittleness. These are the transformer core construction and its properties. Okay, thank you.